Mapping Arctic sea ice surface roughness with multi-angle imaging spectroradiometry. Surface roughness is the standard deviation of elevation measurements within a defined footprint to a best fit plane. It has important applications to climate studies, constraining momentum transfer between atmosphere and ocean, providing preconditioning for summer melt pond extent, and acting as a good proxy for sea ice age. However, pan-Arctic satellite roughnesses have remained elusive and do not extend over multi-decadal timescales. Mizar is an optical satellite on the Terra 1 platform, launched in 1999. It contains 9 camera angles over 4 wavelengths, blue, green, red, and near-infrared, at a resolution of 1.1 kilometers, with 275 meters for the red channel and nadir view, with a swath width of 360 kilometers. It has a 16-day repeat cycle over 233 unique paths, and global coverage is achieved every 9 days. As shown against a wider MODIS swath, the 9 camera angles allow for near-simultaneous sampling of surface anisotropy with a reconnaissance interval of less than 7 minutes. The use of angular reflectance signatures to derive surface roughness has been applied to continental ice using a combination of aftward and forward images known as the Ndai, or Normalized Difference Angular Index. However, on sea ice, the success with this approach has been limited. Crucially, Ndai between different swaths have different statistical distributions and so are not directly comparable. We have created a new processing chain using machine learning to model angular reflectance signatures to quantitative measurements of surface roughness, and applying this on Mizar imagery to produce a novel roughness product. We generate a training dataset of coincident angular reflectance signatures from Mizar and roughness measurements using LiDAR from Icebridge ATM, the airborne topographic mapper. This is then applied to a support vector regression scheme to provide a mapping from specular anisotropy, as sampled from Mizar, to surface roughness. Model performance is assessed and then is applied to individual swaths that can be stacked, generating pan-Arctic roughness maps. In order to derive roughness measurements from Icebridge over a spatially coherent footprint with the 1.1 kilometer resolution from Mizar, probability distribution functions of coincident elevation measurements are generated and the standard deviation calculated. Here we see an example of the elevation point cloud derived for a Mizar pixel left and corresponding probability distribution function right. Only the derived roughness is used for modeling. The training dataset is filtered to remove data that is of poor quality, such as low shot density of elevation measurements, and after applying a feature subset using a sequential forward-floating feature selection scheme, is modeled using support vector regression with a radial basis function kernel. Grid search cross-validation is used to tune the hyperparameters. Model performance is initially assessed using an 80-20 random permutation shuffle split cross-validation. Convergent R-squared scores for the training and testing datasets and mean absolute error approaching the machine error of the ATM are good indicators that overfitting has been avoided through appropriate hyperparameter tuning. Here we see an example of the sea ice surface roughness product that we have created. Here we see our resulting monthly sea ice surface roughness product for the month of April from 2009 to 2019. Each month has been produced by stacking approximately 480 individual roughness swaths. Now we will move on to some potential applications. This product is particularly adept at distinguishing newly formed sea ice, and thus is a good tool for visualizing polynyas. Below we present a surface roughness time series of the North Water polynya. Note the development of northern arches in 2009 and 10, and southern arches in 2011 and 12. Our monthly gridded mean roughness maps exhibit good qualitative agreement with SMOS sea ice thickness. We present a new sea ice surface roughness product from calibration of LiDAR elevation measurements from the ATM with angular reflectance signatures from Mizar. High spatial and temporal resolution is achieved. Model validated by cross-validation and shows good agreement with SMOS. Some thin cirrus cloud contamination exists. This is either easily noticeable on a swath level or averages out in the monthly gridded products.